So let me then go to the first page. So the first page is basically to say that I will not be covering basic principles for the simple reason that I did not invent any of them, and that the inventors should speak for themselves. Now, when I say inventors, I'm thinking mostly about Malcolm and his team in Southampton, but also by the late Ivanov and Novosibirsk, and there's some other contributions from Harvard and elsewhere. I picked 5 basic issues which I trust Malcolm will speak about on another occasion. One is the quest for molecules that have a very long-lived state, possibly immersed in particular environments, such as C60 molecules, cages, and things like that. Then there are technical issues like how you convert magnetization to singlet. There's a so-called M2S sequence, which comes from Southampton that we have used. There is an interesting question of extremely low frequency excitation that also came from Southampton that we converted into so-called long-lived coherences at high field. And then there's a very intriguing paper some years ago on how to classify decay rates according to the eigenvalues in the Liouvillian. So for those of you a bit scared about quantum mechanics, I would leave this to Malcolm to explain, but I will use these ideas. And then more recently, the group in Southampton has written interesting papers about the lifetimes and what controls the lifetimes of long-lived states. So let me just say a few words about what singlets and triplet states are. First of all, on the right-hand side here, I copied this from the book of Peter Hall. And this gives you just a 2-spin system. So in the very weakly coupled limit, when the J coupling is smaller than the difference in chemical shifts, you have a typical AX system. When the chemical shifts move closer together, they turn into an AB with the inner line strengthening and the outer lines weakening. And ultimately, when the chemical shifts, the relative chemical shifts go to 0, you have just a single line. And this is the case where the 2 spins become magnetically equivalent. And then the alpha and beta, the alpha beta and beta alpha states will combine in such a way that you have either the sum of them, which makes the central triplet state, or the difference, which is the isolated singlet state. And typically these are drawn like in the bottom corner here. We have the 3 triplet states. The central one is almost adjourned with the singlet state, except for a slight shift given by J. And then tentatively already introduced here the concept of populations. This is a population distribution that you would expect at very, very low spin temperature, in fact, 0 degree Kelvin, where all the populations would concentrate in the bottom state. That is more a Gedanken experiment than anything else. Now, if we have a completely equivalent system of 2 spins, the Hamiltonian is very simple. It's just J times vector I dot vector S, or if you prefer XX plus YY plus ZZ, and that is the Hamiltonian. But it is also the only term in the density operator. And of course, these two commute, which implies that the Hamiltonian has no effect. Now, this time of Hamiltonian can occur either when we have no magnetic field, or if the spins are magnetically equivalent, as in my drawing from Peter Hall, which means that they should have the same chemical shifts, but also the same couplings to all other nuclei in the molecule. The third option is that the chemical shifts can be suppressed by spin locking. We sometimes call this sustaining in our jargon. And the fourth option is that you can suppress them by rapid sequences of refocusing pulses in the manner of Corpuscle. Now, rather than citing from my own work, I'd like this review here from my former student Simone Cavadini and my former postdoc, now Professor Paul Vassos, and the student Leticia Fernandez, who worked with Paul Vassos while he was professor in Paris. He now moved to Romania. You find this in the Encyclopedia of Magnetic Resonance, and there is a very nice illustration here, which shows one of the PET molecules that we had asked a friend to synthesize, which is basically a sugar, protected sugar with lots of deuterons, and only 2 non-deuterated protons that form an AB or an AX system. These are, technically speaking, diastereotopic protons, because there are several stereogenic carbons in the vicinity, and you can excite a long-lived state or a singlet state, which is the same thing, between these 2 protons. And you see the decay is very, very slow of this long-lived state, on the order of 20 seconds or so, whereas the inversion recovery, the standard T1 that everybody knows how to do, takes only maybe a second or so for the T1 to cause the recovery of the magnetization. So there's a factor of 20 or 30 or something between the T1 and the long-lived state, which is very convenient. Now, this is also taken from this Vassos review. Here you have an arbitrary molecule with 2 protons. There should be different substituents R1 and R2, and at least one of them should have a stereogenic center so that these are not degenerate. And initially, you have a population distribution like this, where the black balls represent an excess population with respect to the demagnetized state. The top state has a deficiency population, and the intermediate states have neither one nor the other. So this is the Boltzmann equilibrium and thermal equilibrium. And then you do some encoding sequence. There are several different ways of doing it, but the basic idea is to overpopulate the singlet state and spread the population among the 3 triplet states, perhaps evenly, or anyway, make a different population on the right-hand side than on the left-hand side. This is also known as a population imbalance, a very nice, simple word that Malcolm invented some years ago, which will be a guidance also in this lecture. Now, of course, although in principle this can last forever, in practice it will relax. So as you wait for relaxation, you will see some of these black balls disappear and will cancel the white balls in the triplet state. And then you have to decode this, because in itself it's not visible, to generate a new distribution of populations within the triplet manifold, and this can be observed as a spectrum. Now, in practice, you can do this with various pulse sequences. This is one of our favorites in the early days, the so-called Sarkar sequence. It comes from a student called Sarkar in Lausanne, but it's Levitt who gave this name, for 2 weekly couple spins. And so what you do is you excite a magnetization, you allow them to, well, you refocus the chemical shifts, but you allow the J coupling to evolve. This tau1 and tau2, the 2 tau1 intervals are both equal to 1/2J. And then you apply not a 90-degree pulse, as you would, for example, in inadequate or in inept, but a 45-degree pulse. And then you allow a certain time here, because in that period you have a superposition of ZZ order, which doesn't move, and 0 quantum coherence, which does evolve. And this has to evolve to a certain angle before you switch on the continuous RF field, which is applied, a weak RF field in the middle between the 2 chemical shifts of the spins I and S. And this has the effect of converting the product states into triplet and singlet states. And then this is where the lifetime can be measured and is the interesting variable. Once you switch it off, you do the sequence in reverse and you end up observing a signal. And you can embellish this by applying so-called bipolar pulse gradients in order to label the position of the molecule within the sample tube at the beginning and at the end, and that gives you access to diffusion. And you can also do variants. This is again from the Vassos review, slightly the same picture, top picture, but the slower picture is now different. In this case, we don't go through long-lived states, but we go through long-lived coherences, which basically are 0 quantum transitions between the central triplet state and the isolated singlet state. So it seems to be strange that you can create such a forbidden 0 quantum coherence, but in fact, it's quite convenient. But my lecture will not talk about that too much today. Now, yes, so the first application, I actually identified 6. Some of them will take a few slides, some of them only 1 slide, so this will be a quick job. Slow diffusion can be done by, first of all, conventional stimulated echo diffusion autospectroscopy. This is something that was being invented years ago. It's a similar sequence as before, except that you convert the transverse magnetization to populations by 90-degree pulse. And these populations, which have coherence order 0, you allow them to migrate through diffusion over a period uppercase delta. And then you convert them back into a signal by a reversed sequence. You have a pair of pulsed field gradients here and here, And the point is that the diffusion allows the molecule to migrate through the sample so that it will experience different intensity of the field here than it did here. And that allows it to measure the diffusion. Now, the signal that you see here, S, can be compared with S0, which is the signal that you have if there are no gradients applied. And that follows an exponential law, where kappa here is the product of gamma. That's usually the proton, because that's the best one. The coherence order, the shape of the gradient, and the maximum intensity of these black gradients here, times the duration of these gradients. And as you can see, this follows, if you do it experimentally, it follows a nicely Gaussian curve. And of course, the interesting observable that this interesting parameter that we want to extract is D, the diffusion coefficient. But we have to be aware of the fact that the signal is attenuated, both S and S0 are both attenuated by this exponential decay according to the T1. And T1 can be too short, or rather the diffusion can be slow compared to T1, in which case the sequence doesn't work. So very early on, soon after Malcolm came with his singlet state papers, we developed a slow diffusion singlet state variant. So this is the same that you just saw, and this is the variant that we developed, where you basically apply a radio frequency pulse during this continuous spin locking pulse during the diffusion interval delta, after having prepared long-lived state. And you can see that you get similar curves like this, and you see, here it is. But the main difference is that now the signal is attenuated by an exponential function of minus delta over TLLS, which is much longer than the T1 that we have up here. So you can compare the two, and this is again from the review. This is another review from Cavadini and Vassos in Concepts. And they studied the diffusion of this simple molecule, which has two inequivalent protons, dissolves at the MSO so that it gets nice and sticky if you lower the temperature, very viscous. And you can see that what they did here is that you can have a much smaller kappa. So kappa is, among other things, proportional to the gradient amplitude, which of course cannot be infinitely strong. And you see that with conventional stimulated echoes, this kappa parameter had to go to 4,000 to measure the full decay, whereas here we could go to 300, which is less than a factor 10, or better than a factor 10 short, lesser in amplitude. And then in addition, here we had a diffusion delay of only 200 milliseconds, and here it's become 20 seconds. So again, this is a considerable, much longer. So you have a double advantage of using longer delta, that means slower, that you can observe diffuse species that's diffuse slower, and smaller kappa, meaning that you can get away with weaker gradients. Now, the next item that I picked from a long list is the idea of watching enzymatic reactions by creating a long-lived state in the substrate. I fear that there are not many examples, but this one is, I think, a textbook example, and it was developed by Aurélien Bornet, was the main subject of his thesis in Lausanne, of course, with the help of Zhao Ji, Daniel Mamouni, Basil Pichou, Jonas, and Sami Janin, who is now professor doing very nice work in Lyon. Anyway, they started with fumarate, which is this particular molecule, and if we assume that all the carbons are C12, none of them is carbon 13, and the oxygen's oxygen 16, then these two protons are strictly magnetically equivalent. In fact, they're so equivalent that it would be almost possible to generate a singlet state between them. I don't know of any high field technique, except by going to very, very low spin temperatures, which you can do with dissolution DNP. So we could achieve spin temperatures on the order of 10 millikelvin or so. And then you can have an unbalance between the triplet and the singlet state. This imbalance will last forever because this has probably, well, T1 or TLLS, that may be minutes or even hours. But the interesting thing is that if you have a reaction where a fumarase, which is an enzyme that would be present at very low concentration in D2O, then it turns out that you have an addition of water molecule, the heavy water molecule, ending up with a molecule where you have one deuteron here, sorry. To avoid at all costs. I'm afraid that I'm using an unusual. Here we're back again. So never click on your mouse. We have one deuteron here and an OD here. So this molecule is completely asymmetric and unsymmetric. These two protons are quite inequivalent and they form an AX system. And consequently, the singlet state that was locked in this totally symmetric molecule is now suddenly released and spontaneously converted to observable magnetization. And you can watch the growth of the signal, which is proportional to the growth of the concentration. If you ignore the fact that it, of course, relaxes like all things do in NMR. So this is an interesting way of monitoring the kinetics of a reaction. Now, to come to the same thing, in fumarate, we had a pure triplet completely separated from the singlet. After the reaction with fumarate, we ended up with a weakly coupled two-spin system, and it turns out that this black population remains in the bottom state, but this combination of a deficiency in the singlet state and an excess in the triplet state turns into a shared, well, slight deficiencies on these two central states. So you can imagine what kind of signal you can extract from there by applying a small flip angle pulse. This is in fact a ZZ order. Now, another problem that we talked about a great deal, both in Lausanne and in Paris, is how can you tackle many spins? Well, Malcolm has also worked on this, but I would like to give one example here of this particular molecule, where you have two nearby protons, which have a strong dipole-dipole interaction. So these would be an interesting candidate to create a longer state. But we have a third proton that perturbs here, and of course that will participate and somehow contribute to the relaxation of the other two protons and basically break the symmetry and mess the whole thing up. So the question is, what do we do in such a case? Well, we postulated that mostly the longest state would be made between I and R, and therefore, mathematically, this would be a product of the vector I times the vector R. So this is Ix, Iy, Iz, and this is Rx, Iy, Rz, and this is the scalar product between the two. But it turns out that the longest state is not pure like this. It's a superposition of this thing, but also a little bit of Is, that is the long-lived state between this proton and this proton here. And there's also that mixture of Sr, which is a long-lived state between the two protons on the same side. And you can convince yourself by diagonalizing the Liouvillian that these coefficients lambda are the dominant coefficient is, as we expected, 0.93 here. But there is also 0.23 for this term here and a 0.28 contribution for this term here. So we call this a quadratic term because all three constituents are bilinear operators, but the coefficients are non-trivial, as you can see. Then we also thought, hey, there might be a cubic term, and the initial intuition was it might be a T, that means a tertiary term or a cubic, whatever, would be a product I, X, S, X, RX. But after doing a more careful analysis, it turned out that indeed there is such a thing with a coefficient mu0, which is 0.5 in this case, but it is, shall we say, contaminated by a superposition, a sum of a little bit of Is, from which you have to subtract some of the unity operator multiplied by Rx. So this is again a cubic term minus dx, and a little bit of a term that comes to the IR product and another term from the SR product. So we have a rather complicated state with coefficients that you can calculate by diagonalization of the Liouvillian, for which, by the way, you have to know the geometry of the molecule in the first place and also the motion as represented by spectral densities. So you need a lot of information to be able to calculate these coefficients. But that is not particularly relevant because if you create one of them, the system will project automatically into these eigen operators. So the next picture is I took from a work in physical review letters by Stephen Devines, Walsworth, and Rosen. This is a very beautiful paper, which I have overlooked for many years, unfortunately, but it gives a very nice way of creating longer states between strongly coupled systems, which is something that the Sarkar sequence does not achieve very well. And there was a very nice idea from the Levitt group, which is called magnetization-to-singlet, and which comprises a number of pi pulses. In fact, it's maybe 10 of these and then 5 of these or something like that, depending on the strength of this system coupling. But De Wiens and company invented another idea, which they called spin-lock-induced crossing, or SLIC. And this uses simply a 90-degree excitation pulse followed by a phase shift from Y to X, and then a continuous RF field, a little bit like in hard cross-polarization, except that in this case, the amplitude of this field has to be matched precisely with a J coupling between the two spins, between which you would like to excite a long-lived state. And then you allow that to evolve. There's no need to apply a field typically, and you can use another spin lock to bring it back into magnetization. A very beautiful paper. This was used or adapted, if you will, by a number of people in Novosibirsk. The first author, Kirill, is now in my lab in Lausanne. You also note, sorry, in Paris. You also note that Konstantin late regretted Ivanov was one of the key authors of this work. Alexandra Yokovskaya, who is now running the team after his untimely death. This was published some years ago in Scientific Reports, and it's an interesting case of this azobenzene, which was enriched in N15. And it turns out that you can create a long-lived state between these two N15s if you start by exciting the protons, the orthoprotons of the two rings. And it turns out that by only applying RF field to the protons, you can create a long-lived state of the two nitrogens and apply another singlet to multiplet conversion to get a nitrogen signal after this. So this is one of many possibilities. And you notice then that you get a very, very long decay, very slow decay. In this case, the longest state is on the order of 1,000 seconds, which is much, much longer, about 250 times longer than the T1 of these nitrogens. Among other things, because the T1 is affected by the CSA of the nitrogens, whereas the long-lived state is not, because the two CSA tensors happen to be aligned in this case. And that is a very favorable situation. So I recommend reading this paper as well. Then I would like to move to systems containing quadrupolar nuclei. So that's rather counterintuitive because quadrupolar nuclei tend to relax very quickly, and therefore you would not expect there to be any long-lived states. But Thomas Kress and Dennis Kurzbach with Astrid Walrand have shown that it can be done in a peculiar way. So what you see here is a multiplet, in fact there are 7 lines in it, of a methyl group that is contains a carbon-13 in natural abundance, but that was completely deuterated. So, and this was also polarized under DMP conditions at low temperature, about 1 Kelvin, prior to being injected into a 400 megahertz spectrometer, and then we observed the decay of the amplitude because of relaxation after hyperpolarization. But the interesting thing, well, then Kurzbach pointed out that such CD3 groups are actually quite common in drugs. Sometimes deuterated drugs have better properties than normal drugs. They could be less toxic, or they can have a better lifetime in the organism, a slower enzymatic metabolism. So that's interesting. But that's for the pharmaceutical people. For the NMR people, we just retain that there are 7 lines. So this is a triplet of a triplet of a triplet, in each case with equal splitting and equal amplitude, 111 triplets. And if you look at the energy level diagrams, then you realize that for these here on the left side, there are 27 states that all belong to the carbon alpha, and there's another 27 states that all belong to the carbon beta. And these can be classified according to symmetry. Technically speaking, in group theory, these are called irreducible representations, but we can just call them A, B, and E. And the lines, the carbon-13 lines, go between the C alpha manifold and the C beta manifold. So for example, this blue transition here is between the bottom state here and the bottom state here, and that gives the leftmost line that you see here. These two blue transitions are essentially superimposed, and they contribute to the L2 line, etc. The point now is that we can overpopulate these red states because at very low spin temperatures, ideally if you go to 0 Kelvin, only this bottom state will be populated and everything else will depopulate. So that's the idea of using DMP to create a population imbalance. Now you can use all these amplitudes to back calculate the populations, one of the contributions of Ivanov. And then you can set up, you can define a population of the A manifold, normalize it by the population of the same manifold, minus the population of the E manifold, also normalized, divided by the sum of these populations. And we call this the long-lived state, referring to the deuterated system. And you can now calculate with redshift theory what the decay should be of this long-lived state. And it turns out to have a rate, and this rate is a slightly messy expression, which contains both tau c, which is the tumbling time of the molecule, and tau r, which is the internal rotation time, lifetime of the methyl rotation. If tau c is if tau r is much shorter than tau c, this is clearly a misprint, then you can eliminate tau c from this, and you retain the fact that the long-lived state has a rate that is directly proportional to the lifetime of the rotor in any one of its positions. So, but there is, of course, some leakage, and the leakage comes from symmetry breaking mechanisms. And that would occur if your deuterated methyl group encounters another molecule, for example, a protein. And this was used to see if the population balances are affected by the encounter of the DMSO, which is the hyperpolarized deuterated methyl group that we talk about, when it meets a protein such as BSA. If there's no protein, then you see the PA manifold is slightly overpopulated and decreases after dissolution, whilst the PE manifold is underpopulated and goes back to its equilibrium after dissolution. But in the presence of BSA, you see that this process goes much faster. In fact, the initial slope here shows that this takes about 3 seconds, which is remarkably long for a quadrupolar system, whereas in the presence of a protein, it reduces to about 1.5 seconds. And if you add trypsin instead of BSA, it turns out to be about the same, which was a bit surprising. We thought one of these two proteins would have no interaction, but it does. Now, let me take another subject, which is one of our favorites, parawater. It turns out that there should be long-lived states in water, H2O, which you could call parawater, just like we speak about parahydrogen. But these long-lived states are very, very difficult to get your fingers on. Nevertheless, we wrote a paper on this, although it was not very conclusive, to tell you the honest truth. And the idea is that at very low spin temperatures, you can create a state where most of the population is concentrated in the bottom triplet state, so that the singlet state is depopulated, at least partly, and therefore there is a population imbalance. Now, it turns out that in the solid state, at about 1.2 Kelvin in a field of 6.7 Tesla, this was done in Lausanne in a heroic series by Sami Janin and collaborators. It turns out that instead of having a symmetrical doublet, you have a very asymmetrical doublet. I'll try to prove that this asymmetry here is evidence that at 1 Kelvin, 1.2 Kelvin, we actually had parawater, at least part of it. But before to prove that, I have to make a little bit of an excursion and briefly go to another paper, which is about deuterium NMR. So this is a single deuteron, ideally, at low temperature, at about 1 Kelvin. And to explain this, I have to say, before discussing symmetry, that for a single deuteron, we have no singlet state, but only a triplet. And there are 2 single quantum transitions, and they are split by the quadrupolar coupling. So you have a doublet like this for a given orientation. And in a frozen glass, you have all sorts of orientations. And it turns out that you have a distribution of quadrupolar splitting from positive to negative. And when you add them all up, weighted by their probability, then you get a typical powder pattern, which is known as a Pake pattern. Now, normally at high temperature, at room temperature, the Pake pattern is strictly symmetrical. But if you go to very low temperatures, only the bottom state is populated, or at least to a first approximation. And therefore, if you use small flip angles, don't ever use a 90-degree pulse for this kind of thing, say a 10-degree flip angle, you will have mostly this coherence, a transverse magnetization in the bottom transition, but very little in the top transition. And as a result of that, one of these two doublet components will vanish, or if you prefer, one of these two halls will vanish. Although we never quite managed to get them vanish, we could have very marked asymmetry. And Diego could simulate spectra of this. So the top one is an experimental spectrum, very beautiful, low signal to noise, as you can see. But the simulations show that the asymmetry varies and gets more pronounced as you go to lower temperatures. So these are absolute spin temperatures, not sample temperatures, spin temperatures of the deuterium manifold. And by comparison between the two, or fitting if you like, we figured out that we achieved 3.5 millikelvin. Now, under certain conditions known as thermal mixing in this trade, we can convince ourselves that we should have the same spin temperature for all other nuclei, carbon-13, protons, phosphorus, what have you, but that is yet to be proven. But we believe that we have a similar spin temperature for protons, and if we go back to this, now we see the same doublet that you have already seen, so we can estimate that the spin temperature here is on the order of 2 millikelvin, something like that, and this means that there is a significant overpopulation of the triplet with respect to the singlet in water. So this is just water in DMSO, diluted DMSO, with Tampol, which has the free electrons, frozen, as you can see. On the left, without microwave irradiation, that means that the spin temperature is the same as the sample temperature, whereas on the right-hand side, it is with microwave irradiation, so that we go lower the spin temperature from about 1 Kelvin to about 1 millikelvin. So this is, we believe, para water, at least most of it is para water. The trouble is to get it out, and we have not succeeded to dissolve this solid. For that, we need an aprotic solvent, so not water for sure. We have tried DMSO, but the problem is that DMSO doesn't have sufficient heat capacity to warm up the whole system, and it's less, and it's also viscous and problems like that. So we have not been able to dissolve the sample without destroying the ortho-para imbalance. So although I had an ERC project to do this, we never came quite to a proper conclusion. Now, a final subject, which is close to my heart, in fact, is the use of long-lived states in drug molecules binding to a macromolecular target. Could be a protein or maybe a nucleic acid. So this was described in several papers. The effect was actually initially found by Nicolas Salvi, and sometimes I'd like to speak of the Salvi effect. But in a later paper, we came with this molecule here, which is basically a peptide, glycine, arginine. We know that the arginine has a certain affinity for this protein and will stick it to a binding site. And therefore, if we mix the protein and the arginine, the tumbling time of the arginine will be dramatically reduced. But we didn't look at any of these protons. We attached by a covalent amide bond this bromothiophene, and these two protons turn out to be very convenient because they are weakly coupled, and if you create with using the Sarkar sequence, you create a long-lived state between them. That state is very long-lived. So this is the ligand, this is the drug, if you will, that could become a drug, and this is the protein to which it sticks. Now, if you see these spectra, this is just a proton spectrum of these two red protons here. And if it's just a free ligand, just a drug, you have two doublets. Doublets are not very well resolved because this is after rapid dissolution, so the field is not very good, not very homogeneous. And it turns out that if you add protein, then the intensity of the signal drops. So this is a different sample, and you have to be careful to normalize the signals properly, but we have learned how to do that. And you know that you see that the signal drops dramatically after a certain sustaining interval of the long-lived state. But when you add another molecule called myricetine, which is a competitor with a much stronger affinity, higher affinity, then the protein, then the signal comes back again, because in fact there's a competition of myricetine which will fill the binding sites in the protein and expel our drug molecule, so that most of it is again free. So this is discussed in some more detail in this example. So we have the same molecule here. In black, it's the ligand only. In green, the bottom molecule, the bottom spectrum is 120 micromolar ligand, so that's not very much, and 1.5 micromolar trypsin without competitor. As you can see, this is a dramatic effect, provided we have a rather longish sustaining period of 3 seconds, so that most of the long-lived states will decay. And if we add this competitor, which is something that we learned from Claudio Dalvit, by the way, we recover much of the amplitude, meaning that the ligand has been expelled, meaning that the competitor has a higher affinity than the trypsin, which is an interesting piece of information. In fact, you can, we've also done this with fluorine 19, and in fact, this is a different molecule where these two fluorines are not equivalent because there is a stereogenic carbon a few bonds down the line. And so they have different chemical shifts, and we can use the Sarkar sequence in this case and measure the long-lived state. And the rate of this long-lived state, the decay rate of the long-lived state, is a linear combination of the free rate and the difference between the bound and the free rate, multiplied by this ratio, the concentration of the complex protein ligand divided by the total concentration of ligand. Now, this ratio, as you may have learned in first-year chemistry, can be expressed as a square root of various things. And in this relationship, you find the dissociation constant here, which is, of course, of great interest for pharmaceutical purposes, because the better the drug, the higher the affinity, the smaller the dissociation constant, the better the drug. So what we see here is a titration where this particular crazy molecule has been increased in concentration against the constant background of protein. And you see this gives a very nice curve following this expression and allows you to determine KD very accurately. In fact, we defined this in one of these papers, the contrast. So this is a contrast for a long-lived state experiment, which is the observed rate of the mixture, of which we subtract the rate of the free ligand without protein, divided by the observed ratio, and then multiplied by 100 so that we end up in units of percent. Still the same molecule, the difluorinated molecule, and we, if we do this experiment, we find that under these conditions, the free rate is on the order of 0.4 second, whereas if it's in the presence of 2 micromolar trypsin, it jumps to almost 3 per second. So the contrast, according to this definition here, is about 87%. Now, we were hoping that we could improve on this. In fact, we tried also long-lived coherences, which I briefly alluded to at the beginning of my lecture, rather than long-lived states. And we had, for some reason, the idea that if we define a contrast for long-lived coherences in analogy to the one we had before for long-lived states, then we would have a better result. Well, we did the 2 experiments, long-lived states and long-lived coherences, and see for the states, the populations, the contrast is pretty good, but for the coherences, the contrast is less favorable. So this was not a very good idea, and we have to work on how to improve the long-lived states. But I think there is a take-home, not message, but a take-home question. And I'd like to cite my former teacher, Hans Primas at ETH Zurich, who was also the PhD advisor of Richard Ernst sometime before I met him. And he said the tricky thing in scientific research is to ask a good question. Once you have a good question, it's fairly easy to find an answer. Now, I like this idea, and I've been looking for good questions all my life. And this one here, maybe not a good one, but it's one that keeps me awake at night. Can long-lived states be tailored to provide the highest possible contrast between free and bound ligands? Now, this is a different quest from the quest for the longest lifetimes, for example, or from the whatever property these long-lived states may have. This is a different question. And I note that there is some superficial similarity with what the MRI people call relaxivity. So after this, I would like to show the many people to whom I owe lots of thanks. In fact, this is the group in Paris. The group in Lausanne, I no longer have a picture on my in my lecture, unfortunately. But this is now quite old because it was before COVID. And this morning I wanted to make a updated picture, but as you can see, we were together in a lecture room. We had to be separated by one empty seat for reasons you can imagine. And since everybody wears masks, I thought it was not going to do that much of a favor to ask them to line up and make a group picture with all these half-headed faces. But I also owe a lot to all of these institutions, particularly to the ERC, who gave 2 grants to our group, and in fact 3 with Fabien's and 4 with 2 of Fabien Ferrage, and various institutions that I've listed here. But I would also like to advertise this journal, of which I'm the editor-in-chief, believe it or not. And it has many interesting aspects. First of all, it's open access. Secondly, it's very cheap compared to other open access journals. I have written not long ago an obituary about Richard Ernst for a journal called Chem, and I was told that if I wanted to have it open access, all I needed to pay is £9,400. I decided that was really too expensive, like almost £10,000. But in this journal, you can get away with €75 per page. Typical papers went over 5 or 6 pages, so that's not very expensive. But the most exciting part of it is the interactive reviewing, in the sense that the reviewers can remain anonymous if they wish, but they can also reveal their identity. And more than that, there is quite a lively debate between different readers and different people in the community who have an opinion and criticism. An example of this can be found right now. There's a paper from Philippe on radiation damping, which is currently being debated, and I would like to encourage you to look at the website, which you can find under magnetic resonance ampere of this journal. And now all I have to do is to thank you for your attention. And I think I'm about 45 minutes, but of course it was a bit longer. We started a bit later, so I hope you're still with me. Thank you for your attention.
Thank you very much, Geoffrey, for what was a brilliant talk. And apologies to you again and to the over 100 attendees for your patience. And I think we will now be open for questions.
I would be delighted. Is there some sort of a chat box as well? I can see, yes, there is a chat box. I can open that.
Oh, so we now have a question from an anonymous attendee, which asks, frozen water molecules form strong hydrogen bond coupling networks or a complex spin bath. How do we ensure that the 2 hydrogens are in a para state? Shouldn't the intermolecular coupling be negligible than the J coupling between the 2 hydrogens?
Absolutely. So the dominant dipole-dipole coupling in frozen water is the intramolecular one. The intermolecular one is on average weaker. In our particular sample, the water was heavily diluted in DMSO, deuterated DMSO. So the intermolecular water-water interactions were weak. But they play a role, because if the water were strictly symmetrical at 1 Kelvin in a frozen glass, would still be, the 2 protons would still be magnetically equivalent, and there would be no channel to go from between the triplet and the singlet. So it's a good thing that in the glass, the symmetry of the molecule is broken by virtue of its neighboring molecules, so that we can actually create this imbalance. But as soon as you dilute the sample, then the J coupling takes over, so to speak, and you get an A2 system in the liquid's dominant.
Thank you very much for your answer. Before someone else asks a question, I think I may ask my own, which is you showed very impressive and pioneering applications of spin thermometry in the cryogenic solid state. And I was wondering, what do you think of the prospect of such singlet triplet imbalances existing in systems of other spin half pairs? For example, 13C2 or 15N2 spin systems.
I think the phenomenon should be universal. Spin temperature, as its name suggests, is not related to the nucleus. It's not a function of electromagnetic ratio. it's really a temperature. And having said that, I think the phenomena that we observed are likely to be observable for deuterons, for protons, for nitrogen-15, for carbon-13, ideally for pairs of such nuclei, but not necessarily. So I would say it's possible to do such experiments. It's not completely obvious that it would help you for anything, but I would vividly encourage people to try.
Thank you very much, Geoffrey, for your answer. So we have a question from Nicholas Alby. Comment first. Great talk, Geoffrey. In biomolecular NMR, it is common to use multiple quantum coherences to probe diffusion that is too slow for single quantum probes. For example, the triple quantum coherence-based experiments published by Lewis K. Can you comment on what are the advantages and disadvantages of using long-lived states versus MQ coherences?
Well, MQ coherences are more sensitive to pulsed field gradients. So, for example, if you create the triple quantum coherence, it will be 3 times more sensitive to a pulsed field gradient than a single quantum coherence. So that's a bonus. But apart from that, the lifetime of a multiple quantum coherence is mostly shorter than the lifetime of single quantum coherence. I don't think there is a simple rule about that, but early hopes back in the 80s that multiple quantum coherence would give very sharp lines turned out to be illusions. So I don't think multiple quantum coherence are an ideal way to go, except maybe so that you can label the position more effectively by using weaker pulsed field gradients. But I'm afraid this is a disappointing answer to Nicola, whose work I much appreciate.
Okay, I think we have more questions. One from Ilya Kuprov, which asks, the null space of the relaxation superoperator can be quite rich. We saw by simulation 4-spin and 8-spin singlets. Are you aware of any experimental work in that direction?
May I give a slightly unsatisfactory answer? Yes, I'm aware of it. And in fact, I think we have them. We have prepared them and observed them in our lab last week. But it's perhaps a little bit premature to give the details of how we did that. But I'm aware that there are higher spin states with more spins involved that can sort of cooperate to give long-lived states. In fact, we had an example of these cubic states in a 3-spin system.
Thanks, Geoffrey, for that very exciting answer, actually. I think everyone's looking forward to read that work. We also have another question from an anonymous attendee, which asks, do you think it's possible to create a long-lived electron spin state? Does such a state already exist at dissolution DNP conditions in coupled electron spin radicals? Can such states be used for DNP?
I've never thought of this, but of course, if you have pairs of spin radicals, you do have triplet states, and you do have longer lifetimes than the singlet states. This is, well, you know, intersystem crossing, all that sort of stuff. Lifetimes are important. Whether you can, and in fact, it's very well known. There's nothing new there. Whether you can transfer some of the know-how that we acquired in NMR to do some useful experiments in ESR, I don't know at this point. I think it's an open question, but a very interesting question.
Okay, would anyone else like to ask any questions? So I may ask one of my own. So I'm sure, Geoffrey, that you're aware of some of the very early work in the field by Jean Genet, for example, which I think as early as the 70s showed the existence of a singlet temperature
Yes,
in
I'm aware of
gypsum.
I'm aware of that work. In fact, we studied that.
Yeah, so I was going to ask you as an expert in this field, why do you think it took so long for liquid state Singlets NMR techniques to be developed?
I think you should ask Malcolm, because he was the first to come forward with a way of exciting and observing them. It certainly hadn't crossed my mind at all. In the case of Gener's work in solids, so this is in big patterns in frozen water, the singlet state is, let me say, postulated, and, but it's not really observed. And there is no real recipe of a conversion of an pulse sequence, for example, that would convert the singlet state into an observable or vice versa. So it's highly respectable work. In fact, it's perhaps also one of the papers that may have inspired Malcolm. I think we should ask him rather than me. But it's not one where you have a conversion step. I think one of the fundamental steps that was achieved with the invention of two-dimensional spectroscopy, COSY and such things in the early days, is that you can transfer coherence or spin order from one pool, from one reservoir to another. And I think in the days of George Bake and Jean Genet, that early paper that you mentioned, that concept was not yet mature, not yet worked out. So the transfer of order is now a tool that was not available.
Thank you very much for your insightful answer. And that brings me again to one of my own personal questions, which maybe I'll defer because we have a question from an anonymous attendee. A general question: is there a common ground between a photochemistry group studying radical pair mechanism and LLS groups in NMR? Any thoughts if there is any knowledge transfer possible between them?
I myself have never worked on optical, what is the expression? It has just disappeared, but the sort of systems that you're referring to. But there's a lot of work going on in other labs. I'm thinking primarily of Novosibirsk, where Rob Kaptein has done many papers on call these singlet triplets interconversion in radical pairs, and the effect on proton and nuclear spectra through kidnap effects. And the same group in Novosibirsk has also done a great deal of work on singlet states in just pure nuclear without electrons. So I would imagine if there were transfer of know-how or of inspiration, it would have happened possibly in Novosibirsk or in other groups that have worked on photosynthesis and on electron-electron triplet pairs. But I have no experience with this, so I suggest you address the question to people who are working in that area.
Thank you very much, Geoffrey. Do we have any other questions? Okay, I may take the opportunity to ask one of my own. So we've already talked about in your previous insightful answer, that's one of the pioneering applications of a 2D NMR was showing that these special coherences could be excited and read out. Do you believe that one day this could be done in the solid state as well? For example, exciting and reading out singlet order or long-lived order in general?
Well, we have tried. We, meaning basically only one person, Diego Carnevale, spent at least a year of his precious life trying to excite long-lived states and also long-lived coherences in solids. There are many obstacles. You can imagine internuclear dipole-dipole interaction and other things. And also the problem is that in solids, typically you have to decouple the protons while you're observing the carbons. And Of course, you cannot decouple the protons for very long before the probe goes up in smoke. So long-lived states would have to be in rather dilute systems. We looked at pairs of phosphorus nuclei in a background that has no magnetic nuclei at all. But none of these ideas came to any useful result. But I would very vividly encourage people in the solid state community to try again. To my knowledge, there has been no evidence that long-lived states could be prepared in the sense we're having lifetimes longer than T1. We did look in some detail at water trapped in, like in gypsum, but in our case, we used a salt that we borrowed from Bob Griffin, or rather inspired by his papers, which is a barium chlorate hydrate. And the hydrate molecules are very isolated, and so you can very nicely, like in George Pake's work. And we looked at the T1, and we found that the T1s are very anisotropic, but we could not generate population distribution that would have a longer lifetime than the longest T1 in these anisotropic powders. So it's an interesting problem, probably just purely academic, but as I mentioned, some people have invested a lot of effort so far with little success as far as I'm aware.
Thank you for your answer, Geoffrey. I can also say in our group, we have dreamt of a Singlets NMR in the solid state, and so far it has only been a dream. And we now have a question from an anonymous attendee, which is, has anyone explored long-lived states in doped crystals?
Presumably you mean doped with UV excitable molecules? Is that what you have in mind? Or you mean doped with pyromagnetics? Can you please explain what you mean by doping?
Yeah, can the anonymous attendee give us more detail?
In fact, I think neither. Doping with pyromagnetics obviously reduces the T1s. We all know that, and that is in fact sometimes necessary to avoid the T1s going through the roof. But since we never found any long-lived states that have a lifetime longer than T1, we had no motivation to dope these powders with pyromagnetics. There is a lot of work going on with things like pentacene embedded in naphthalene, which allow you to excite triplet states, electron-electron triplet states. There is a lot of work in that area, but this is probably not what you had in mind when you spoke of doped crystals.
Yeah, so he's clarified and said that yes, doped with actual molecules, for example, in MOF.
Yes, well, we did some NMR on metal oxide frameworks, if that's what you mean by MOF. To my knowledge, I don't think there is any particularly obvious opportunity to excite long-lived states in MOFs. Maybe someone else will find that, but I didn't see any opportunity. If we did, we should certainly jump on that.